And the best place to start is on the very first rung of the ladder, the first dimension.
Right.
Think of this as the real numbers. This is the math you use to balance your checkbook. It's the familiar flat number line you've known your whole life.
Right, the basic stuff.
Exactly. You can line these numbers up, compare them, and put them in a perfect logical order. Like 3 is clearly bigger than 2. -5 is smaller than 0. It is simple, linear, and completely ordered.
It makes perfect sense. One-dimensional math behaves exactly how we want it to, but then we take a step up. We jump from the first dimension to the second dimension.
Yes, so to reach the 2D plane, we introduce a new concept, which is complex numbers. We do this by adding the idea of the square root of -1.
Right. Suddenly, you aren't just moving left and right on a flat line anymore. You can move up and down in an imaginary direction. So it opens up an entirely new, flat plane of mathematical capability.
But, and this is a crucial theme for you to keep in mind as we climb, every time we jump up a rung on this ladder, we have to pay a toll.
Yeah.
Gaining a dimension always comes with a cost.
It does.
And here, in the second dimension, the research points out that we completely lose ordering. Okay, let's unpack this.
Yeah. The first sacrifice is made. In that 2D realm, you can no longer meaningfully say that one number is bigger or smaller than another.
Right.
If I point to a complex number that sits way up and to the left on our new plane, and another that sits down and to the right, asking which one is greater just becomes a nonsense question.
It's exactly like asking if north is bigger than east.
Yes, perfect analogy. The very concept of a universal sequence or order completely evaporates.
So it's a direct trade-off. We gained a brand new dimension to work in, but we lost a fundamental rule.
Yeah.
Let's keep climbing.
According to the mathematics, the system doesn't quite stabilize in the third dimension, so we have to jump straight to the fourth dimension.
The Quaternions.
Right.
The story of how we found this four-dimensional space is actually quite legendary. The biography we reviewed focuses on an Irish mathematician named William Rowan Hamilton.
Yeah, Hammer.
The year was 1843, and Hamilton had been agonizing for years over how to make algebra work in 3 dimensions.
He was just stuck.
Completely stuck. He was literally walking across Brougham Bridge in Dublin, turning the problem over in his head, when the solution struck him like lightning. To make the math function, he needed a 4th dimension.
Wow.
But to unlock it, he realized he had to make a massive sacrifice. He had to give up commutativity.
Okay, let's unpack that too, because I know from grade school that commutativity is the rule that says the order of multiplication doesn't matter. It's the law guaranteeing that A times B is always the exact same as B times A.
Right. But Hamilton realized that in this new 4D space, multiplying A by B gave you a completely different result than multiplying B by A.
That's so weird.
Suddenly, the strict sequence in which you interact with these numbers dictates the actual outcome.
So for you listening, think of commutativity like putting on your clothes. When you're dealing with normal, everyday numbers, it's like putting a hat on your head and a scarf around your neck.
Right, the order doesn't matter.
Exactly. Hat first, scarf first, the end result is the same. But when you move into 4 dimensions, it is absolutely like putting on your socks and shoes. The order absolutely matters.
Very true.
You get a profoundly different and, frankly, potentially disastrous result if you try to do shoes first and socks second.
That visual is spot on. In 4 dimensions, sequence is everything. You cannot swap the order without changing the reality of the math.
Now, even though the order changed in 4D, there was still a comfort there. The grouping of the math still worked.
Yes.
By grouping, I mean a rule called associativity. If you have to multiply 3 things, A, B, and C, it doesn't matter if you tackle A and B first or B and C first, as long as you keep them in the same left to right line.
Right, that rule was safe.
But the ladder keeps going up. What happens when we make the radical jump to the 8th dimension?
This is where we reach a mathematical space called the Octonions, 8 dimensions.
Okay.
And this is where the toll for climbing the ladder gets incredibly steep. To enter the 8th dimension, mathematicians had to sacrifice associativity entirely.
Wait, so you're saying we have to abandon the idea of grouping things together safely. How does a math system even function without that?
It becomes incredibly slippery. In 8D space, you completely lose the ability to group calculations without fundamentally changing the answer.
That's crazy.
It is. If you have 3 separate directional units in this space and you want to multiply them, the result depends entirely on where you place your parentheses.
I think we need a really clear analogy for this because shifting parentheses sounds abstract.
Sure.
Think about it like human language, specifically punctuation and how we group words. Take the sentence, "Let's eat, Grandma."
That's a brilliant way to frame it.
Right. The words are identical. The sequence from left to right is identical, but how you group the words dictates the entire reality of the sentence.
Yeah, absolutely.
If you pause and group the words as, let's eat, pause grandma, you are inviting your sweet grandmother to sit down for a nice dinner.
A lovely evening.
But if you shift the grouping and say, let's eat grandma, you have completely changed the outcome into something terrible.
Very terrible.
The sequence didn't change, but the grouping changed the reality.
That is exactly what happens with octonions. Let's say you are multiplying three values. If you group the first two together, calculate that, and then multiply by the third, you might get a negative result.
Okay.
But if you keep them in the exact same left to right order and simply shift your mental pause, grouping the second and third values together first, the mathematical sign flips completely. Your answer is suddenly positive.
Wait, really? If the final result totally flips from negative to positive just based on how you group the calculation, doesn't that make the system completely useless for any reliable standard calculations?
It definitely seems that way.
Like, how can you build anything on a foundation like that? I mean, standard calculators would essentially have a panic attack.
And what's fascinating here is you're touching on the exact problem that caused mathematicians to largely ignore the octonions for decades.
Really?
Oh yeah, because of this lack of associativity, you cannot represent octonions using standard matrices.
And standard matrices are the bedrock of computer science, right?
They are. Matrix multiplication relies entirely on grouping being consistent. It demands associativity.
Okay.
Take the four-dimensional quaternions we just talked about. Even though the order of multiplication matters to them, the socks and shoes rule grouping still works.
Right, you can still group them.
Because of that, quaternions play incredibly well with matrices. We use 4D quaternions every single day in the real world. They run computer graphics, they orient spacecraft in orbit, and they are used in robotics.
Wow.
They are the standard tool for calculating 3D rotations because they translate perfectly into matrix math.
But the octonions are totally disconnected from that toolkit. They're basically algebraic outcasts. You try to put them in a standard matrix, and the matrix basically rejects them because it expects a consistent grouping that the octonions refuse to provide.
Exactly. They are completely alienated from standard computing tools.
So if they are this weird, and you can't use them with standard matrices to build practical tools, why didn't mathematicians just throw them in the garbage? Aren't they just a mathematical dead end?
Well, useless is a strong word, but a lot of people certainly thought so at first. However, exploring that exact question led to one of the most monumental discoveries in the field, which is Hurwitz's theorem.
Hurwitz's theorem, okay.
It proves that this grouping flaw isn't a dead end at all. It's actually a hard defining boundary of logic itself.
What kind of boundary?
So Hurwitz's theorem proves mathematically that there are exactly 4 and only 4 of these special number systems where you can consistently measure the size of a number and where you can always safely divide by any non-zero number.
Only 4.
That's it. Those 4 systems are exactly the ones we've just climbed. The 1D real numbers, the 2D complex numbers, the 4D quaternions, and the 8D octonions. The list permanently stops there.
Hold on, why does it have to stop there? What happens if a mathematician just stubbornly tries to force the issue, doubles the dimensions again, and jumps to 16 dimensions?
You can theoretically construct a 16-dimensional space. They're called the Sedenians.
Okay.
But at 16D, the whole structural foundation collapses. The cost of entry is simply too high. You introduce what mathematicians call zero divisors.
Zero divisors, that sounds like a mechanical failure.
It is the ultimate mechanical failure for arithmetic. It means you can take 2 completely non-zero entities, multiply them together, and somehow get an answer of absolute zero.
Wait, what? That breaks everything. If you have 2 physical non-zero things, how can multiplying them together yield nothing?
It shatters the concept of division. Think of division like putting a car in reverse. If you multiply 2 things to get a result, division is the gear that lets you back up to where you started.
Right, that makes sense.
But zero divisors are like gears losing their teeth. If non-zero things can multiply to become zero, you can no longer divide numbers to work your way backward. You get stuck. The mathematical structure completely loses its integrity.
Wow. So the takeaway for you listening to this is really profound. The 8D octonion system isn't just some random, quirky puzzle. It is the final, largest complete system of its kind possible in mathematics.
It really is.
Its limitation, that bizarre loss of grouping, isn't just an arbitrary rule. We literally hit the edge of the logical map.
And this is where the research papers get truly fascinating, because the octonions sit right at this unique final boundary of logic. They form incredibly rare, beautiful
Well,
structures.
like what?
Specifically, they require highly constrained ways of rotating objects.
Hmm.
The symmetries that preserve this broken eight-dimensional math form a very special, rigid geometric group.
Right, the research calls this G2, right?
Exactly.
And without getting bogged down in the textbook terminology or having to read out annoying underscore notations, what you really need to know is that G2 acts as an incredibly specific set of rules for how things can rotate and move within a seven-dimensional space.
Yes. It's a geometry that only exists because of the unique structural flaws of the Octonions. And as soon as you start analyzing rigid geometries in seven-dimensional spaces, the theoretical physicists suddenly walk into the room.
Here's where it gets really interesting, because there is a staggering coincidence hidden here.
Oh, yeah.
When you look at superstring theory, which is physics' best attempt to explain all the fundamental forces of reality using microscopic vibrating strings, string theory dictates that our universe can only stably exist in a very specific number of space-time dimensions.
That's right. The math of string theory overwhelmingly demands universes that have 3, 4, 6, or 10 dimensions of spacetime.
Now compare that to our algebraic ladder. The four mathematical algebras we just climbed are 1, 2, 4, and 8 dimensions.
Oh.
The string theory dimensions are 3, 4, 6, and 10. Every single string theory dimension is exactly 2 greater than the algebra dimensions.
It's crazy.
1 becomes 3, 2 becomes 4, 4 becomes 6, 8 becomes 10. It's just perfectly matched.
It is entirely uncanny.
But hold on, let me play devil's advocate here. I am the proxy for the listener's skepticism.
Go for it.
If we only experience 3 dimensions of space and 1 of time in our daily lives, aren't physicists just inventing these extra dimensions to make their broken math work? And why is there a persistent offset of exactly 2?
It's a completely fair question, and the physics papers we read address this directly.
Okay.
The extra dimensions aren't just invented. They are required to balance out the mathematical anomalies of quantum mechanics. And that offset of exactly 2, that comes from the nature of the strings themselves.
How so?
When a tiny string moves through space and time, it sweeps out a two-dimensional surface, known as a world sheet.
Like a sparkler moving through the air at night, leaving a glowing trail. The string itself is one-dimensional, but its movement creates a two-dimensional sheet.
Exactly. That's a great way to picture it. The complex math that governs the vibrations on that 2D world sheet only balances out, only avoids falling apart. If the total dimensions of the surrounding space-time equal the dimensions of one of our 4 algebraic systems, plus the 2 dimensions of the world sheet.
Wow. So 1D math plus the 2D world sheet gives you 3. 8D math plus the 2D world sheet gives you 10. The fundamental structure of these abstract numbers is literally dictating the dimensional rules for the strings that make up our universe.
And the connection deepens even more when we look at M theory.
M theory.
Yeah, which is the overarching framework trying to unify all the different versions of string theory. M theory operates in an 11-dimensional universe.
Right, but again, we only see 4 dimensions, 3 of space, 1 of time. Where are the other 7?
M theory suggests that the universe has to compactify or tightly curl up those extra 7 dimensions into incredibly tiny microscopic spaces.
Curled up spaces.
Think of looking at a garden hose from far away. It looks like a 1D line. But when you get up close, you see it has a circular 2D cross-section curled around it. M theory proposes that at every single point in our visible universe, there are 7 extra dimensions curled up just like that.
But they can't just be crumpled up randomly, right? They have to fold up according to very specific geometric rules to allow our physical reality, the particles and forces we interact with, to exist exactly as they do.
Spot on. And what governs the geometry of those microscopic 7-dimensional spaces?
Don't tell me.
The structure is governed exactly by the G2 symmetry, the exact same rigid geometry born from the Octonions.
Let's synthesize this because it is huge. The constraints and the apparent flaws in this bizarre 8D math perfectly mirror the physical constraints required by our most advanced, cutting-edge theories of the universe.
Yeah.
The math didn't just stumble into alignment with the physics, it laid the foundation. The laws of nature literally require the mathematical brokenness of the Octonions to function.
It really forces you to completely reevaluate what a mathematical flaw even is. It wasn't a failure of human logic. It was a prerequisite for physical reality.
Okay, this is undeniably mind-blowing for understanding the fabric of reality itself, but reading through the engineering articles in our stack of research, it makes me wonder, does this 8-dimensional math have any actual use for us right now?
In the real world, you mean?
Yeah, in the practical real world, because earlier we established you can't use them for matrices or normal 3D programming.
Right. And for a very long time, the answer was a frustrating no. They live purely on chalkboards.
Yeah.
But recently, we are seeing the emergence of highly specialized engineering applications, specifically something called the Octonian Fourier transform.
Okay, let's unpack that.
Oh,
What does an Octonian Fourier transform actually do?
let's explain how this works conceptually. We live in a world overflowing with dense data. Imagine an engineer is trying to process a highly complex signal. Let's say it's a high-definition color video feed for an autonomous drone, but it's simultaneously combined with 5 other independent sensor streams,
Like what kind of streams?
like thermal imaging, depth perception, audio, radar, and motion tracking.
Gotcha.
So that's 8 distinct, heavy channels of data flowing all at once.
Normally, using standard parallel processing, an engineer would have to process those 8 channels separately.
Right.
It would be like having 8 different translators listening to a chaotic conversation, translating their own piece, and then trying to sync all their notes together at the end. It takes a huge amount of computing power to figure out how the streams relate to each other.
That's the perfect analogy. Parallel processing struggles to see how the channels interact in real time. But because octonions are naturally fundamentally 8-dimensional entities, engineers can use the Octonian Fourier transform to treat those 8 separate streams as a single, unified 8-dimensional object.
So instead of 8 separate translators, you have one mathematically profound translator that understands the entire 8-dimensional language holistically.
Yes, the math rotates and analyzes the entire block of data at once. By processing it holistically, the Octonian math preserves the intricate correlations and relationships between the thermal data, the depth data, and the video feed that parallel processing might miss or struggle to sync.
That is brilliant. You are literally leveraging the unique non-associated 8D structure to perform multi-layered data analysis in a single stroke.
Exactly.
It proves the math isn't just a theoretical toy for physicists. The brokenness actually creates a highly specific tool for understanding complex interconnected data in the real world.
It's a niche field right now, but it's growing rapidly. It shows that pushing past the boundaries of standard logic yields actual tangible benefits.
So what does this all mean for you, the listener? Let's wrap up this journey. We started with a very simple, innocent idea. Let's just keep extending the number line. Let's see what happens if we add more dimensions.
A simple curiosity.
But that pure curiosity forced mathematicians to climb an invisible ladder that demanded heavier and heavier tolls. We lost ordering.
Right.
We lost commutativity. And eventually, we had to sacrifice a fundamental rule of grade school arithmetic associativity. We had to accept a grammatical nightmare of a math system where the mere grouping of the numbers completely changed the reality of the answer.
But by accepting that steep cost, we didn't hit a dead end. We discovered the ultimate logical boundary of number systems.
Exactly. That very flaw defined the edge of mathematical possibility. It gave birth to exceptional geometries, and it perfectly, uncannily mirrored the hidden dimensional structures required by string theory to explain our universe.
Incredible.
And now it's even helping engineers process massive streams of holistic data for advanced robotics.
It really asks us to challenge everything we take for granted. I'd like to leave you with a final thought to mull over. We go through our lives assuming that the universe is fundamentally logical, straightforward, and associative. We assume that the order in which underlying reality groups its interactions doesn't really matter, as long as all the same pieces are present.
That A and B interacting with C is exactly the same as A interacting with B and C.
But the Octonians suggest otherwise. They suggest that at the very bottom of reality, at the absolute deepest layer of the quantum world, that assumption might be entirely false.
Wow.
What if the most foundational laws of nature operate on a grammar where the grouping of events fundamentally changes the fabric of reality itself? If the blueprint of our physical universe is built on a mathematical system that our own standard computers consider functionally broken, what else in our universe, what other strange phenomena or limitations we observe every day, might actually be perfectly broken by design?
It makes you wonder how many other flaws in the world are actually hidden features we just don't understand yet.